Hello everyone, I am Parthiban, working as an assistant professor in Bisabibar College. Today I am going to talk about analytic functions in complex analysis. First, let us see the content of my lecture. First, we can see neighborhood and limit of a function and continuous function and then derivative of a function, and finally we can see analytic function. First, we see the definition of neighborhood in complex plane. A neighborhood of a point A in complex plane is a disk around a within a specified radius r greater than 0. Neighborhood is a set of all collections, a point from the distance to A whenever whenever the distance is less than r. Next, the limit of a complex valued function. The limit of f of z as z tends to z naught is defined as limit z tends to z naught f of z is equal to L. If for every epsilon greater than 0 there exists a delta greater than 0 such that modulus of f of z minus L is less than epsilon whenever 0 is less than modulus z minus z naught is less than delta. As z closer to z naught, f of z approaches L. There is a difference between a real variable and a complex variable. In the real variable, the way of approaching z tends to z naught is two, one from the left and one from the right. In the complex variable, there are infinity number of ways. For example, there is the ways come from 360 degrees. The limit value should be the same as z approaches z naught from any direction. So let us see the example for limit. Here we can apply directly z is equal to 1 as z in the function z square. We can directly get 1. We can easily verify that as per the definition of epsilon delta, we can also verify that the limit value is 1. Here is as we discussed earlier, the limit values should same as z tends to z naught as per any direction. Here we have take two direction. From the right we get the limit value 1, and from the left direction we get the limit value minus 1. So the two limit values are different. So hence we can conclude that the limit value does not exist. Next we move on to the continuous function definition. A function f of z is continuous at z naught if z tends to z naught, f of z equal to f of z naught. This definition is equal to the definition of limit. Here we can replace that the L should be f of z naught. Let us see the example. The function is continuous because the limit values f of z naught is equal to 3 plus I. Let us see the non-example for the continuous function. Let us take the function f of z equal to 1 by z. The function is undefined at z equal to 0. So the function is not continuous at z equal to 0. Let us see the definition of derivative of a function. The derivative of f at z naught is defined as f dash of z naught is equal to limit z tends to z naught f of z minus f of z naught by z minus z naught. The limit value exists and it should be finite, and it is called a derivative of a function at the point z naught. Let us see the example. Let us take the function f of z equal to z square. We can use the above formula. F dash of z naught is equal to limit z tends to z naught, z square minus z naught square by z minus z naught. We find the limit value to z naught. Before we enter into the non-example of differentiable function, let us discuss about the Cauchy-Riemann equations. It is a necessary condition that whether the given function is differentiable or not. And also it is also sufficient when the partial derivatives are continuous. So let us see the non-example. Consider the function f of z is equal to modulus z square. We can find the partial derivatives dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y of real and imaginary parts respectively. We can see that the Cauchy-Riemann equations are not satisfied. Hence, the function is not differentiable. Let us see the analytic function definition. A function f of z is analytic at z naught if it is differentiable at z naught and in some neighborhood around z naught. Let us see the example. Let us take the same example, f of z is equal to z square. We can see that easily verify that the CR equations are satisfied and the partial derivatives are continuous. So we can conclude that the function differentiable everywhere in the complex plane. So we can say that the function z square is an analytic function. Let us see the non-example. As we discussed in the non-example of a differentiable derivative of a function, here also the CR equations are not satisfied. So the function is nowhere differentiable. So we conclude that the function is not analytic. Conclusion of my lecture, continuity, differentiability and analyticity are hierarchical properties in complex analysis. Not all continuous functions are differentiable and not all differentiable functions are analytic. Analytic functions from the cornerstone of complex analysis with applications in physics, engineering and applied mathematics. Thank you.